Welcome to this seminar series. And this talk, the first talk this morning, this afternoon, will be given by Professor Zhiyong, Xiao Zhiyong 教授. And he is now a professor at the Xiao University in Zhuhai, China. And was just talking to him, and I realized that he got his PhD from the China University of Geosciences in Wuhan, China. But during his graduate study, he went to Arizona to visit Professor Bob Strong there for 2 years. So I would say that he is also he's basically also Bob's student and learn everything from Bob, I hope. And then subsequently, after finishing, he went to Oslo to work for as a postdoc for Professor Stephanie Werner. I think Professor Werner is an expert on the lunar crater chronology, and she has given a talk already in the early part of this seminar series. And now Professor Xiao is settling down at the Xiao University. I think that he's doing well, and he's built up his group, and we expect many very interesting results coming from his group. Professor Xiao, okay, it's yours now.
Thank you, Professor Yip. It's my great honor to join the seminar, and especially for me from Xiao University, because I'm from the lab called the Planetary Environmental and Astrobiological Research Laboratory. So we call it a Pearl, and this name was given by Professor Yip when he was visiting us in 2017. At that time, I was still working at China University of Geosciences at Wuhan. Very fast, and we deeply appreciate the help of Professor Yip, not only our lab, but also the development of planetary science in China in general. So today I'm going to present a talk called Lunar Crater Chronology, Perspective from an Outlier. And when I gave that name, the title of the presentation was pretty harsh. I said, oh, I shouldn't do this because nobody wants to hear about a story by an outlier. I call myself an outlier because I didn't publish many papers on calibrating the lunar chronology, but I have a great interest on this topic, and I'm waiting for my turn to have a big one. So since the audience have attended many lectures about lunar sciences, I guess everybody is familiar with the surface topography of the moon, that impact craters are the dominant landforms on the surface of the moon. And people should already know that crater counts has been a major technique used to estimate the surface ages for the moon and also beyond. And the basic story or the basic theory behind body, if the crater higher than the other one, then that means it was exposed for a longer time. So it was either formed or resurfaced or emplaced earlier than the other one. So the relative age can be pretty easily get for units on the same body to compare the crater size frequency distribution on them. So here shows a comparison for 3 different crater populations on different aged surfaces. One is on the highland that is entirely occupied by various impact craters and impact basins, and the others are for the lunar maria, where we can see that the vertical axis is the crater density. The highland has a much higher crater density than the lunar maria. So it's pretty simple or pretty easy to get the relative ages for different trains. But if we want to move further, can we get an absolute model ages? It's possible if we know the cratering rate. That means if we know the formation rate of impact craters with different sizes. So if we know this, then we can use the observed crater density on the surface to divide the cratering rate to get a model age. So this basic theory was established in the 1960s officially, And actually, people were starting to do that in 1940s. So this technique, when established in 1960s, has becoming the dominant or the major technique used to estimate surfaces, ages for planetary surfaces, not only the moon. So there are two most important functions in the theory. One is called it crate production function. Another one is called it crate chronology function. So crate production function is about the relationship between the density and different size craters that were formed within a given time interval. So for example, this production can mean the size frequency distribution of all craters formed within the last 1 billion years or 2 billion years. So this function was established by Loicum when he studied the crater size frequency distribution on different aged surfaces on the moon. So here shows a color mosaic of the lunar surface, where we can see different colors frequent usually means surfaces in place at different ages. If we do get the crater size frequency distribution and we normalize to a same function, we can see that their cumulative crater size frequency distribution can be normalized to a given same function. So that's more or less means for surfaces on the moon that were formed at these ages, the production function has been more or less stable. They can be described using a single production function. So that's one part, means the craters formed in the history of the moon has been stable. Another key part is chronology function, which is a function of surface ages, different ages surface. So as you see that this means the number or the density of craters larger than 1 kilometer in diameter in a given surface. But this number, the size of diameter can be changed arbitrarily because we can use the production function. So the key parts for the chronology function are the observed crater density on the Lunar and Apollo sampling sites, and also the ages for the samples retained. So if we use the two functions together, we are able to get an isochronous. That means we are able to get the size frequency distribution of impact craters that were formed at different time intervals. So for application, if we want to use this system to estimate the model age for a surface where low samples were obtained, we can simply connect the craters on the surface and then fit them to the isochronous, so we can get a best fit for the model age. So that's how we do that, and that's how most planetary geologists estimate surface ages. So is that simple? I always say that the formation of impact craters on a given surface is more or less like the dropping rainbows, the raindrops on the surface. But people frequently know that the formation rate of raindrops on a mud pond is not so reliable. You have many issues that can affect the formation rates of different raindrops, and that's also exactly true for the formation of impact craters as well. However, the first order reliability of this technique has been verified for several times already on both the moon and Mars. I'm going to take two examples. One is that before the Apollo samples were retained, before we actually get a sample from the moon, people were wondering what's the composition of the lunar material, and he had an idea at that time back to 1961. At that time, we already know several impact craters on the Earth, and many impact craters were accumulated in the Northern America, and we know their ages. So he estimated the crater density at the Northern America, and then compare this density to their model ages, to model age of the Northern American craton. And then he transferred these formation rates of impact craters on Earth to the formation rates of impact craters on the moon. And then he used telescope data to count craters on the lunar Maria, and then he get an age for the lunar Maria, saying that this surface was in place at about 3.6 billion years ago. And when Apollo samples were returned from the lunar Maria, the data are exactly, on the first order, they're exactly the same. So that's a very good story to say that, this theory can more or less get a reliable age remotely for the planetary surface. Another one is for Mars. It has been interesting that since people realize meteorites, some meteorites on Earth were ejected from Mars, they were curious to know that the sample ages are very, very young. Most of them are less than 1 billion years. So the lava flows and the basalts on Mars, most of them were placed within the last 1 billion years. And when they use the production transfer that Moon have accepted the same impact population, you can estimate the formation rates or impact craters on Mars, and then the estimated surface ages for most units of Mars, they are very young and they are consistent with the isotopic ages measured in lab for the Martian meteorites. So because of the successful tests, the lunar crater chronology has now been extended to all the other terrestrial planets and even beyond the snow line. So in literature, we can frequently see applications of crater chronology on Vesta series and even some icy satellites. However, there are two fundamental assumptions that have to made to make sure that this technology is reliable. One is that we have to assume that we know the impact flux. That means the crater chronology function. We have to assume that this chronology function is correct. Population is stable in the history, so we can use the same production function to estimate surface ages for different units. So that's two assumptions. But in reality, nature is much more complicated than the assumptions. So before the Apollo, the samples were returned from the moon by Apollo missions. Telescope data already revealed the large crater density difference between the lunar Highland and the lunar Maria, which is plotted here. So the average density on the lunar Highland is about 32 times that of on the lunar Maria. Since we already get a model age for the lunar Maria before the Apollo mission, which is 3.6 billion years ago, that means in the first 1 billion years of the moon, the impact flux was much higher than that after 3.6 billion years. And another obstacles that was witnessed immediately after samples were returned, isotopic ages for the samples are constant around 3.9 billion years. And they are low. Actually, before 1970s, there were no samples that were older than 4.1, very few of them. So at that time, people may think that there must have been an intense bombardment around 3.9. So that has resettled the surface ages and get the peaked concentration of the isotopic ages. And also observation of the crater size frequency distribution on both the moon and the other terrestrial bodies found that on each of the inner solar system bodies, there are two populations of impact craters on the surface. On older surfaces, that is divided about 3.8 billion years ago, surfaces older than that age, their size frequency that have a totally different shape to those. And if we use the crater scaling laws to translate the crater diameters back to the diameters of impactors, and we can see that for the older populations, that is so-called population 1, the size frequency distribution of the impactors are comparable with that of the main belt asteroids today. Another thing is that the younger crater population formed after 3.8 billion years ago, their impactors have a more or less similar crater size frequency distribution with the near-Earth objects that are observed today. So this leads to a science paper in 2005 claiming that there are two populations in the inner solar system. So that means the production population doesn't follow the same size frequency distribution. So basically, it means we cannot use a single production function. The people may be wondering that what's the difference between the two? So here you get a normalized cumulative crater frequency, and here you get an R value. So the two are basically the same. So they're same data sets, but use the different methods to present the size frequency distribution. As we can see that the cumulative size frequency distribution has removed many detailed changes in the shape of the curves. And so when we study the shape of the populations, we frequently using R plots. That's the difference. And at almost the same time, an old idea was proposed around 2005 to explain the observed different populations on the inner solar system bodies. Is that, you know, people back to the end of 20th century, people already noticed, including distinguishing some changes may occur pretty late in the history of solar system. So there were evidence from the structure of the Kuiper belt that the planet Neptune was once much closer to the sun. So there must be some later dynamics that was happening in the solar system that had changed the structure of the orbits for the planets. So to explain the possible peaked isotopic sample ages on the moon around 3.9 billion years ago, and also the two populations were observed. So in 2005, a famous dynamic model was proposed called the NIS model. That actually includes a large range of different models in their simulations. So their models can explain the dynamics of the solar system bodies to explain the peaked formation of large impact basins. So that was used to explain the concentrated isotopic ages for lunar samples. And they can also explain the shape of the crater size frequency distribution observed on the lunar highlands. But as many of you are very well known that the dynamic models can have a lot of arbitrarily assigned parameters to explain the required observations. So this is also a very highly dynamic field. And let's see how it changed after 2005. So there are always different ideas compared to the peaked impact flux around 3.9 billion years ago, which is called late heavy bombardment. But we have to be careful that the name of late heavy bombardment has different meanings in literatures, and many people have just mistakenly used late heavy bombardment as the terminal cataclysm. So late heavy bombardment means after most of the planets have formed at their present orbit, and there were some intense bombardment happening in the solar system. Bombardment is called the late cataclysm. That was the most of the evidence. Based on most of the evidence we have talked, that, you know, the lunar samples were concentrated at about 3.9 billion years for the isotopic ages. So terminal cataclysm is one end member of the late heavy bombardment. At the same time, you know, at the same time, people have believed that the cratering history in the inner solar system was much simple we do not need to involve the different populations or the unconstant or the sudden increase of impact flux. So that's the gradual decline of impact rate caused by the continuous accumulation of planetesimals that were slowly veneered to the parent body. So that's the two competing theory ever since the lunar samples were retained. And I have to say that before 2005, at around 2005, the theory of the scenario of the terminal cataclysm was more popular at that time. But now the Intel scenarios, different scenarios have changed frequently, including now. So I have to say that most people start to agree a single population, and there's definitely no terminal cataclysm. They were maybe need heavy bombardment. So that's the present prevailing theory in this field. So let's check what evidence do we get. So Professor Ip has mentioned that the observations from the highly cytosphere elements, the concentration in the mantle of the Earth and also the Moon, that were used as evidence to argue against or argue for the existence of late heavy bombardment, especially the terminal cataclysm. But now more and more evidence are saying that the original idea that during the crystallization, during the cooling of the magma ocean, most of the HSE, high cytosphere elements, they will be merged into the, differentiated into the core. So the content we are observing today in the mantle and the crust, they were largely caused by the accumulation of conjugated materials. So if we know the content of HSEs in the mantle, we know how many conjugated materials have accumulated in the body, and then we can use this as an observational constraint to estimate how many objects has merged into the body. So that's the used as a observational constraint. They were an updated published in 2017, and in many literatures that's claimed to be much better than all the other models that were published before. But Barroso, from Japan, they are claiming that they have another better one. Since I call myself an outlier because I do not understand which one is more advantage in terms of the orbital physics, but I'm going to comment on them. So using this model, the dynamic model of estimating the formation rates of different impactors, including asteroids, the black line, and also comets, the green line, and also the accumulation of leftover planetesimal during the creation of the planets, they can compare with the observed crater densities on different aged surfaces. They can fit the observation by different theories that include late heavy bombardment that using the cataclysm and the member scenario to compare with the concentration of HSE in the mantle. So if we follow this late heavy bombardment or cataclysm scenario, that will means that most of the impact basins formed before about 3.9 billion years ago, they were largely formed by comets instead of asteroids from the main belt. However, in all the lunar samples and retained from by Apollo and the lunar missions, and also the meteorites, there were strong evidence of enrichment of cometary material in the samples. So that's used to argue against the cataclysm scenario. On the other hand, if we assume that the highly cytosphere elements in the mantle, they were not only veneered by post-lunar magma ocean impactors. Many of the elements, they may be inherited from the primary mantle, when the moon or the other planets were formed. So that's a geochemical evidence saying that many HSEs in the mantle, they can be inherited. They were not completely differentiated during the magma ocean phase. So in that case, we do not need so many chondritic materials to accumulate after the magma ocean phase. If we follow using this scenario, and this scenario was proposed in 2016, and the scenario works for the Earth. It was designed for the Earth, not for the Moon. But in 2018, Movidani, and also the major author on the 2016 Nature paper, they assume that the same scenario, that some HSEs can be inherited from the primary materials. They use the observed content of HSE as constraints to estimate the impact rate of different sources. And to fit the observation, they find that a single decline scenario by the leftover planesmels can explain the early bombardment history pretty well, and later contribution of asteroids is not so important actually in the formation of the impact craters. And the contribution of cometary materials can be very minor. It can be it's not significant compared to the contribution by the leftover planesmers. So you follow this scenario, we do not need the cataclysm impact bombardment, and the old ideas proposed and advocated by Bill Hartman and Gerard Neukom may be true, that we just need a single gradually declining planesmels to explain all the observed impact record. Get from different lunar samples like meteorites, impact glasses, and also some additional evidence from asteroids, meteorites that were originated from asteroids. During the Apollo era, people noticed that most of the samples were peaked around 3.9 billion years ago, but more and more ages that occurred before 4 billion years ago has been found. So that means there should be more impacts before 4 billion years ago. However, we should be cautious that, for there are still huge bridges between different communities. For people studying meteorites, just such as one of my postdoc, when she was finding a shocked age in the melt, and then she will, propose that, that can be corresponding to a basin impact based on additional evidences. It's also like a joke that in planetary science, when we cannot explain something, we can always include an impact that really can kill everything. And also the glass beads that were formed by the cooling of impact products, just like impact melt and impact vapor. They have different distribution ages. There seems to be a small peak around 3.7 billion years ago, but there are some more pronounced peaks after about 1 billion years ago. So, the distribution of the isotopic ages for lunar glass are not so consistent with the late heavy bombardment scenario as well. And also for the evidence from the asteroidal meteorites, they do not show typical concentration around 3.9 billion years ago as well, but there are several minor peaks around about 500 million years and more cluster ages before 4 billion years ago. We should know that the meteorite ages have different geological meanings with the retended sample ages from the moon by Apollo and Lunar, because the meteorites, they do not have geological context. They do not represent typical impact cratering events. So we can only explain them to be caused by impact, or at most extreme cases ascribe them to basin or large impacts. But we do not know which crater or which event that corresponds to. This issue is also very obvious in the Lunar science. Also, we have very good control. We think we have very good control on the geological context of the samples retained. So here shows the several large impact basins on the moon, and also the location of samples taken from the moon by Apollo and the Lunar missions. Immediately, we can close to Imbrium and Nectaris. Because most of the samples were taken from the surface, which are dominated by lunar regoliths, and in nature, they are a combination of fine materials and also various impact bridges. So impact bridges represent highly mixed materials. How to ascribe to a single fragments or single bridge samples to a given basin forming impacts has been very tricky, and that has been there have been intense debatements about which sample belongs or may be formed by which event. And the same thing is true for the isotopic ages. When we get the radiometric ages from the samples, usually they're from the impact melt veins or certain minerals. We have different ideas and different interpretations that which impact events they may represent. So, among the papers published on MAPS and the GCAs, we can always see such intense debatements. The most obvious debate is about what's the contribution of the previous slides showing the create chronology function that many ages were clustered around about 3.9 billion years ago. And the sampling sites were within about 1.5 radii from the rim of Imbrium. So Warren-Tell Basin is much smaller than the Imbrium Basin. One is about 1,600 kilometers in diameter, another is about 970 kilometers in diameter. So for Warren-Tell, we already know that their distal ejecta, many of them contain a high concentration of impact melt and have a near global distribution, including the Chang'e 4 landing site here. So if the same impact physics should also work for the Imbrium Basin, that would mean that the Imbrium Basin would have resurfaced a large portion of the lunar surface around it, and all the sampling sites may have been seriously affected by this event. So the question is, are we repeatedly dating Imbrium? For example, the Apollo 16 landing site is far away from, but still the ages were all concentrated around 3.9, and nearby they can even see evidence that were possibly shaped by Imbrium during the formation of its secondary impacts. So if we have an overview of all the radiometric ages for the lunar samples, and the ideas has been proposed in literatures about the provenance of the samples. So there's more or less the consensus that the Imbrium Basin was likely formed around 3.92 to 3.94 billion years ago. This is more or less like a consensus now in literatures. But regarding the other basins, so here is a list of water basins larger than about 650 kilometers in diameters, and the assigned stratigraphic ages were based on the cross-cutting relationship, and the N20, N64 are the density of superposed impact craters. So here is an assumed formation sequence for the major impact basins have intense debates among literatures. For example, Nectaris, which is Nectaris. Okay, let me see, which is Nubium here, the beginning of the Nectarian age. So the ages have people have different ideas about the radiometric ages from 4.2 to 3.95. Warren-Tell, the youngest large 1,000 kilometer size impact basin, on the moon also have different interpreted radiometric ages from about 3.85 to 3.6 billion years ago. However, the stratigraphic relationship between the impact basins suggests that there are about 14 to 17 impact basins larger than 500 kilometers in diameter on the moon. So during this short period from about 4.2 to 3.6 billion years ago. If we use the Earth to Moon impact ratio of 20, that means during the formation of Imbrium to Oriental, between about 3.92, Earth science community is very interested on the formation rates of impact basins during that time, because that can be related with the initiation of plate tectonics and the origin of life on Earth. And recently, we have the available of high-resolution gravity data on the moon can reveal many buried impact structures beneath the Maria basalts. So the results suggest that the impact history was even more intensive than we think. So now with more and more buried impact structures were formed, the formation rates or the superposed crater density on the major impact basins can be constrained better. So now we know that between Nictaris and Oriental, we may have 17 basins larger than 500 kilometers in diameter have been formed on the moon. And if we compare the them to the non-stratigraphic ages that were assigned by cross-cutting relationship, which are shown here, pre-Nectarian, Nectarian, Imbrium. And we can see a lot of different information that can be resolved by Grail mission than previous surface evidence that Serenitatis may be as young as Imbrium, Chrysum is even younger than Imbrium, and previous studies will suggest that Chrysum is much older than Imbrium, and the Nictaris basin is close to Imbrium. So if we follow this density relationship, it seems that the impact bombardment, the flux impact bombardment between Nictaris and Oriental can be even more fierce than the cataclysm theory would indicate it. So where are we now? That's 2018 already. How about the crater populations? Do we still have populations now? Using the KS test populations, the size distribution of them. And they find that the initiation time of the so-called innate heavy bombardment may be much earlier than 3.9. They may have been occurred before about 4.1 billion years ago. So that was proposed in 2012, but immediately people would argue that no, you are counting craters that are in equilibrium, because back to 1970s, people already noticed that when you have a continuous accumulation of impact craters, then you will saturate, or say you will equilibrate the crater populations. In statistics, that means the formation of single impact crater would basically means the erasure of same size crater that has already been formed. So the crater density observed wouldn't be changed. If to remedy the effect of equilibrium, people proposed an idea that for each of the each crater form, do that for each of the impact craters connected, and then we will get an effective areas that were not affected by the burial of impact ejecta. So using this algorithm, they found that the different populations, the different shapes of crater size distributions were actually not existed. So the downturn at small diameters is simply caused by the effect of burial formed by earlier impacts. So that's back to 1918. Also in 2019, people argue against this algorithm, saying that if we do this, then there will be zero affected areas on the heavily cratered twins. That's the three curves are coming from. So in practice, this method may not be usable. So they employed a group of scholars from United States. they included a statistical method that used in astronomy to estimate the spatial distribution of impact craters on the heavily cratered trains on the southern. Those less than 40 kilometers in diameter, that means those start to show downturn in the crater size frequency distribution have a uniform distribution. So that distribution is not caused by obliteration. It represents the production function, the production population when it was formed. So this paper still supports the existence of the two populations. And for our site in our group, we haven't published the paper yet, but we have been looking closely into the equilibrium issue, because for the old surfaces, the equilibrium may has definitely occurred, but we do not know in which diameter range the craters haven't been in saturation or in equilibrium. So what does people usually do in previous works? Usually, people will get the size frequency distribution of impact craters on the surface, and then they will compare the densities with some empirical saturation level. So, for example, the 1% geometric saturation level or 10% geometric saturation level. And when the size frequency distribution observed hits the saturation line, they will say, okay, the craters less than this will be in equilibrium. If we use the highest saturation line, that would mean that impact craters on the moon will be entirely saturated down to about 500 kilometers in diameters. That means all craters, the observed density do not represent the real density. So this is a very serious issue. If we use 1% geometric saturation level, that would mean that all the impact craters, all the impact structures on the lunar highland are in equilibrium. So what we did, we didn't use only empirical saturation level, and we did a gradual approach from the youngest to the oldest train on the moon. That's why we haven't published paper yet. So the first idea was proposed in 2015, that how can we reliably evaluate the real equilibrium state of a given population. So we'll approach this from the youngest population to the oldest one. We study the production function first, and then we, based on the theory of equilibrium, we evaluate the saturation state for each of the crater populations. So the work was started in 2018, actually at this time, because the idea was to use equilibrium to evaluate that what's the impact flux around 3.9 billion years ago. So we choose several key impact basins: Warrentel, Imbrium, and Nectarius, which is represented by Kidney plains. And we study the crater size frequency distribution on them. And then Nectarius basin, their equilibrium diameters are not identical. And also, they are not so different compared with older trains, the most heavily cratered trains on the moon. That is much larger than 20 kilometers, much larger than 20 kilometers. So this point will be here or there. So the three key points derived here contains a lot of information. That Warrentel is definitely younger than Imbrium, but Kidney plain may not be the same age with the Imbrium basin, like most of literatures believe. So they may be slightly older than Imbrium. If that is caused by Nectarius, that would mean that Nectarius and Imbrium would have the similar age. So that came to the end of this session. I just realized that I do not have time to go to the younger sessions. The problem for the chronology after 3.9, but I will try to have give you a brief idea about what the problem exists there. So did heavy bombardment occurred at all on the moon or the other inner solar system bodies? The answer is yes, because we definitely know that the formation of Imbrium and Warrentel, they have similar ages, and they have the formation of 2,000 kilometer diameter basin at a short time means there's intense and late bombardment. But the initiation, duration, flux changes, and